Have you ever just stopped and wondered what makes your phone, your laptop, pretty much every digital device you own so unbelievably fast? Well, it's not just one single thing, but there is this one brilliant trick, really an idea borrowed from the past that makes it all possible. And today, we're going to break down exactly how that works.
I mean, it really is amazing when you think about it, right? You can be streaming music, you're checking your email, you're getting directions from the map, all at the same time. The secret to that isn't just one super fast part doing everything. Nope. It's a really clever process, an idea that was actually inspired by the Industrial Revolution. So to really appreciate the genius of the solution, we first have to understand the problem it was solving. So let's take a look at the old way, the inefficient way of getting things done. Just one single task from start to finish before you even think about starting the next one.
Okay, imagine a coffee shop, right? But there's only one barista, and they make one coffee at a time, completely from start to finish. So they gather the ingredients, they grind the beans, they brew it, add the milk, serve it, and only after that first customer has their coffee in hand does the barista even turn to the next person in line. It's methodical, sure, but it is painfully slow. And this is exactly how early computers used to work.
But then, computer engineers borrowed this brilliant idea straight from the factory floor, the assembly line. What if, instead of one person doing everything, you break the job down into stages and have different stations working in parallel? This simple shift in thinking, it changes absolutely everything. And in the world of computing, we call this a pipelined microprocessor. The real genius here isn't about making any single step faster. It's all about getting incredible speed through overlap. Think about it. As soon as one task moves from station 1 to station 2, a brand new task can start right behind it at station 1. It creates this constant flowing stream of work. So what are the stages on this CPU assembly line? Well, any basic computer instruction goes through a few key steps. First, the processor has to fetch the instruction from memory. It's got to grab the to-do list, right? Then it has to decode it to figure out what it's supposed to do. Is this an addition problem, subtraction, something else? Next, it executes the command, does the actual math. And finally, it has to write back the result so it can be used later. 4 distinct stages for every single instruction. All right, now that we have our assembly line and we know our stages, let's see how this actually creates all that speed. This is where the magic really starts to happen. So what we're going to do is track 3 separate instructions. We'll just call them instruction 1, 2, and 3 as they move through our 4-stage pipeline. That's fetch, decode, execute, and write back. And what I want you to do is pay really close attention to the overlap. Okay, look at cycle 1. The first instruction is fetched. Simple enough. Now, watch what happens in cycle 2. As instruction 1 moves on to the decode stage, the fetch unit is now free, so it immediately grabs instruction 2. And by cycle 3, look at that. Every single stage is busy working on a different instruction at the exact same time. This is that overlap in action. The pipeline stays full, work is constantly getting done, all the way through to cycle 6 when that last instruction finally finishes. So what's the result? Just 6 clock cycles to finish all 3 instructions. Now, let's compare that for a second. Without pipelining, it would take 4 cycles for the first instruction, then another 4 for the second, and 4 for the third. That's a total of 12 cycles. By simply overlapping the work, we've literally cut the execution time in half. That is the incredible power of the pipeline. But, it's really important to be precise about what we mean by speed here. We didn't actually make the processor's clock run faster, and we didn't make any single stage of the work quicker. So what did we actually improve? Well, this brings us to a super important distinction: throughput versus latency. Latency is the total time it takes for one single instruction to get all the way through the pipeline. And that didn't really change. It still took 4 cycles. But throughput, that's the total number of instructions we can finish over a period of time, that went through the roof. We're just completing way more work per second, and that is the true power of pipelining. Now, there's actually a fundamental rule in computer science that explains this perfectly. It basically says that your overall speed up is always limited by the slowest part of your process that you can't improve. Pipelining is so incredibly powerful because it directly attacks that core bottleneck, the time wasted between instructions. This whole principle, it's formally known as Amdahl's law. Of course, no assembly line is ever perfect, right? Sometimes things go wrong and the whole production line has to grind to a halt. In the world of CPUs, these jams have a name. They're called hazards. There are three main types you'll run into. First, you've got data hazards. This is when one instruction needs a result from a previous one that isn't finished yet. It's like an assembly station waiting for a part that's still being built down the line. Then you have control hazards. These come from forks in the road, like an if-then statement in your code. The pipeline has to pause because it doesn't know which path to start loading instructions from. And finally, structural hazards. This is just a resource conflict, like when two different instructions try to use the exact same piece of hardware at the exact same time.
So, as you can imagine, engineers have spent decades coming up with clever ways to solve these hazards and keep the line moving. And all that effort just shows how absolutely crucial pipelining is. In fact, this one single idea is so fundamental that it has shaped almost every other major decision in modern computer design. And you can see this influence nowhere clearer than in the great debate between two design philosophies, CISC and RISC. You can think of CISC as a toolbox with lots of really complex, specialized tools. They're powerful, sure, but they're all different shapes and sizes, which makes them really hard to fit on a smooth-running assembly line. RISC, on the other hand, it's like giving the processor a set of small, simple, uniform tools. And why do that? Because these simple, identical instructions flow through a pipeline perfectly, like identical little boxes on a conveyor belt. This whole philosophy even changes how the foreman of the CPU, the control unit, is built. To keep that pipeline moving at top speed, RISC processors often use what's called a hardwired control unit. It is incredibly fast, but it's very rigid. CISC processors, since they're dealing with more complexity, often use a more flexible but slower microprogrammed unit. But again, the choice is driven by one thing: how do we best feed the pipeline? So here's the bottom line. From your smartphone and your laptop to the giant servers that run the internet, this one elegant idea, the assembly line for instructions, is the invisible engine that's driving all of modern technology. It was never about doing one thing faster. It was always about doing millions of things at once, all perfectly choreographed. It's an idea that has really defined computer performance for half a century. Which, it leaves us with a final, pretty fascinating question. As we keep pushing the limits of what's possible, what brilliant idea is going to become the next assembly line for computing? It's a fun question to think about. Thanks for exploring this with me.